Welcome to the Sleepy Scholar. It's lovely to have you here tonight. Settle in wherever you are. Maybe you're lying in the dark with the blankets pulled up to your chin, the room gone quiet around you. Maybe there's a lamp still on somewhere, throwing a soft, warm circle against the wall, and you keep meaning to reach over and switch it off. Maybe you're on a train or a couch, or you've got one earbud in and your eyes already half closed. It doesn't matter. You're here, and that's enough. Get comfortable, let your shoulders drop, let the day go. And before we begin our slow wander tonight, let me ask you something I always like to ask. Where in the world are you listening from? What time is it in your corner of the night? I find it lovely to imagine all of you scattered across the planet, all settling down at once to think about the same strange and beautiful thing. So if you feel like it, leave a little note and tell me. I read them and they make this sleepy little channel feel a great deal less lonely. And speaking of that, if you enjoy these slow journeys and you'd like more of them to drift off to, a gentle like and a subscribe really does help. Small creators like me lean on it more than you'd think. And to those of you already subscribed, who come back night after night, thank you, truly. You're the reason the lamp stays on. Now, a small promise before we go any further. We are going to move slowly tonight. There is no hurry, none at all. I'm not going to ask you to concentrate or to remember anything or to follow every twist. If your mind wanders, let it. If you drift off somewhere in the middle and miss the ending, that's perfectly fine. The ideas will still be here when you wake. The universe has been doing this for 13 billion years. It can wait for you. So you have my permission right from the start to simply let go. I will, as always, try not to make this so interesting that it keeps you awake. Though I'll be honest, tonight that might be a tall order. But if it does keep you up, well, at least you'll have learned something strange and wonderful about the dark. A fair trade, I think. So, let me set something down in front of you. A single picture to hold in your mind as you drift. Imagine a box, just an ordinary box about the size of a room. The room you're in, perhaps. Now imagine I told you that the air inside that box was hotter than the surface of the sun, 1,000,000 degrees, hotter than the center of a furnace, hotter than the glowing core of molten rock deep in the earth. 1,000,000 degrees, you'd expect to feel it, wouldn't you? You'd expect it to roar, to glow, to scald the walls and turn everything inside to vapor in an instant. And yet, if you reached your hand into that box, you would feel nothing at all, no warmth, no glow, nothing. It would feel to your skin like the emptiest, coldest, most perfect vacuum you could ever imagine. Better than any vacuum a laboratory on Earth has ever made, and nothing so complete that the best machines we've built can't come close to it. 1,000,000 degrees and empty, both at once, the same place, the same instant, searingly hot and almost perfectly empty. That sounds like a contradiction, doesn't it? It sounds like I'm making it up, like a riddle with no answer. And I promise you, by the end of our slow wander together, that riddle will come apart gently in your hands and make perfect, peaceful sense. There's no need to grasp it now, just let it sit there, glowing quietly at the edge of your thoughts. A few stray atoms, scattered so thinly you could barely call them present at all, and yet each one moving so fast that by the only honest measure we have, the place is hotter than a star. This is real. This is not a thought experiment. This is the actual stuff that fills the vast dark spaces between the galaxies. The places, as the old saying goes, where there are no stars. And here is the thing I want to walk you toward tonight, slowly, one soft step at a time. That dark, between the galaxies nothing. The part of the universe that looks emptiest, that has no stars to light it, that we tend to picture as pure and absolute void, that nothing is where most of the ordinary universe actually lives. There is more ordinary matter out there in the dark between the galaxies than there is inside all the galaxies put together. All the stars, all the planets, all the swirling clouds of gas inside every galaxy you've ever seen in a photograph. Add every bit of it up, and it's still the minority. Still the smaller share. The galaxies, it turns out, are not the ocean. They're the foam riding on top of it. But I'm getting ahead of myself. We have all night. Let me go back and start where the story really starts. Not with the answer, but with the picture in our heads that the answer had to break. For a very long time, you see, we had a beautiful and tidy way of imagining the universe, and like a lot of beautiful, tidy ideas, it was mostly wrong. Not wrong in a way that anyone should feel foolish about. Wrong in the way that the flat-looking ground beneath your feet is wrong. It's a perfectly reasonable thing to believe right up until you learn to see a little further. Back in the early days of the last century, when astronomers were first beginning to understand that the faint, fuzzy smudges they saw in their telescopes were not just clouds of gas inside our own galaxy, but entire other galaxies, vast and far away, they reached for a phrase to describe them. They called them island universes. Island universes, isn't that a lovely image? Each galaxy a glittering island of stars, complete and self-contained, floating alone in an endless dark sea of absolutely nothing. Pinpricks of light marooned in the void, separated by oceans of pure emptiness. The stars and the warmth and the substance all gathered up inside those bright islands, and between them, nothing at all. True nothing, empty space in the most literal sense. It's an idea that just feels right, doesn't it? You look up at a clear night sky, and that's exactly what it seems to be. Scattered points of light, and between them, black, dark, empty. The stuff is in the stars, and the space between is just the stage they sit on, an empty backdrop, a void to be crossed. I want you to hold that picture for a moment. The galaxies as bright, lonely islands floating in a sea of perfect emptiness. It's comforting in a way. Tidy, everything in its place. The light here, the dark there, and a clean boundary between. And then very gently I want you to let it go, because the universe, as it so often does, turned out to be far stranger and far fuller than that. Now you might think the great mystery here, under the thing that overturned the tidy picture, is one of those famous puzzles you've heard whispered about. Dark matter, dark energy. The mysterious stuff that nobody can see and nobody fully understands. The great unsolved riddles of the cosmos. You've probably heard the numbers. If you add up everything in the universe, all the energy and all the matter, the ordinary stuff, the stuff that you and I and the stars and the planets are made of, that ordinary stuff is only about 5% of the whole. A tiny sliver. The rest, the other 95%, is dark matter and dark energy, the great unknowns. And those are wonderful mysteries. We could spend 100 nights on them. But here's the strange and lovely thing, and I want you to really feel the weight of it as you drift. Tonight's mystery isn't about the mysterious 95% at all. Tonight's mystery is about the ordinary 5%, the part we thought we understood. The simple, familiar stuff, the atoms, the protons and neutrons, the matter that builds stars and worlds and bodies and breath. That's all we're talking about tonight. Not the exotic dark stuff, but the plain old ordinary matter that you'd think we'd have a perfectly good handle on by now. And the scandal, and I do mean a genuine scandal, a real and embarrassing mystery that troubled astronomers for the better part of 2 decades, is this. For a very long time, we couldn't find half of it. Half of the ordinary matter, the plain, simple, well-understood 5%, we knew with real confidence how much of it there ought to be in the universe. We had counted it twice over by 2 completely different methods and both agreed. And then when we went looking for it, when we actually tried to point our telescopes at it and add it all up, fully half of it simply wasn't there. It had gone missing, lost, unaccounted for, vanished from the books. Astronomers gave it a name. The way they always do when something refuses to behave, they called it the missing baryon problem. Now baryon, there's a word that might make you want to drift right off, and that's perfectly all right. But it's a simpler word than it sounds. A baryon is just the technical name for ordinary matter. Protons and neutrons, the little particles that sit in the heart of every atom, the building blocks of everything solid and familiar. When a physicist says baryons, they just mean the ordinary stuff. You, me, the chair, the stars. So when I say the missing baryon problem, I really just mean this. Half of the universe's ordinary atoms had gone missing, and for years, nobody knew where they'd gone. Let me slow down here, because I want you to feel just how strange that is. This isn't a case of not understanding something exotic and far away. This is a case of losing track of the most ordinary thing there is. Imagine a banker who knows, absolutely knows, exactly how much money was deposited into the bank, knows it by two separate independent accountings that agree to the penny, and then goes to count the cash in the vault and finds only half of it. Not stolen exactly, not gone, just not where it was supposed to be. Somewhere. But where? That was the puzzle. So let me show you how we knew the money should have been there in the first place. Because the strangest part of this whole story is that we were so very sure of the total, even while we couldn't find half the pieces. We knew the total from two places. Two completely separate witnesses looking at the universe in two utterly different ways, who nonetheless told exactly the same story. The first witness is the oldest light in existence. It has a name, the cosmic microwave background, and it is quite simply the afterglow of the Big Bang itself. Picture this softly. A very, very long time ago, about 13.5 billion years, the entire universe was a hot, dense, glowing fog. Everywhere, in every direction, a blinding sea of light and heat, packed so tightly that light couldn't even travel freely. It just bounced around, trapped, like sunlight lost inside a thick bank of cloud. And then, as the universe expanded and cooled, like breath cooling on a cold morning, that fog finally thinned enough for the light to break free and stream outward. And it's been streaming ever since, traveling for 13.5 billion years, stretched and cooled along the way by the expansion of space, until now it arrives at us not as blinding light but as a faint, cold whisper of microwaves coming from every direction in the sky at once. That whisper is the cosmic microwave background, the baby photograph of the universe, the oldest light there is. And here's the wonderful part. Frozen into that ancient light are tiny patterns, faint ripples and patches, places where the early universe was a hair denser or a hair thinner than its surroundings. And the exact size and shape of those ripples tells us with extraordinary precision what the universe was made of when that light set out. How much ordinary matter, how much dark matter, how much of everything. A spacecraft called the Planck satellite spent years mapping that ancient light across the whole sky in exquisite detail, measuring those ripples with a precision that would have seemed like magic to astronomers a generation before. And from those measurements we got a number. A firm, confident number for how much ordinary matter, how many baryons, the universe contains. That ordinary matter, the Planck satellite told us, makes up right around 5% of everything. So that's witness number one, the afterglow of the Big Bang, measured by a satellite, telling us the total with great confidence. And the second witness is, if anything, even more remarkable because it comes from the very first few minutes of the universe's existence. It's called Big Bang nucleosynthesis. Another mouthful, I know. Let it wash over you. It simply means the making of the atomic nuclei in the Big Bang. In those first few minutes, when the whole universe was hotter than the inside of any star, the very first elements were forged. Protons and neutrons, fresh from the fire, slammed together and stuck, building the lightest elements, hydrogen and helium, and the faintest trace of a few others. And here's the elegant part. How much of each element got made depended very sensitively on exactly how many ordinary particles were crowded into that early furnace. A little denser, and the recipe comes out one way. A little thinner, and it comes out another. So by measuring the proportions of those ancient elements that still drift through the universe today, by reading the recipe, as it were, in the oldest, most pristine gas we can find, we can work backwards and figure out how many baryons there must have been. And here is the thing that should make the hair on your arm stand up just a little in the quiet dark. These two witnesses have nothing whatsoever to do with one another. One reads the afterglow of the Big Bang from 13.5 billion years ago. The other reads the chemical recipe cooked up in the first few minutes of time. Completely different physics, completely different measurements, completely different parts of cosmic history. And they agree, beautifully, right around 5% ordinary matter, the same number from both. Two strangers questioned in separate rooms telling the very same story. So when two utterly independent witnesses agree that precisely you believe them, we were sure of the total, bone sure the universe had a certain amount of ordinary matter in it, and we knew to good precision how much. And so naturally, astronomers set out to find it, to point their telescopes at the nearby universe, the part close enough to see clearly, the part we could actually take a proper census of, and add it all up, to count the stars in all the galaxies, to weigh the great clouds of gas, to tally the hot gas glowing in galaxy clusters and the cold clouds of hydrogen drifting in between. Everything, every kind of ordinary matter they could detect and measure. And then they would add it all up, compare it to the number the two witnesses had given them, and confirm that the books balanced. Except the books did not balance. They added up everything they could see, every star, every galaxy, every glowing cloud and cold drift of gas in the nearby universe. And when they finished counting, when they totaled it all and compared it to the ledger, they had found only about half of the ordinary matter, the plain, simple 5% stuff. About 1/3 to 40% of it in the local universe was simply unaccounted for. Not a rounding error, not a small discrepancy, a vast glaring gap where a huge fraction of the ordinary atoms in the universe ought to have been and weren't. I want you to sit with that for a moment gently as you lie there in the dark. We knew by two separate and trustworthy methods exactly how much ordinary matter the universe should contain. And when we went to find it, fully half of it had vanished. Not the mysterious dark matter that nobody understands, not the strange dark energy, the ordinary stuff, the atoms, the same kind of atoms that make up your hand resting on the blanket, your slow breath, the warmth of you in the dark. Half of all of it in the local universe missing. Where do you lose half a universe? That's the question that sat unanswered for the better part of 20 years, and it's the question we're going to follow slowly and softly tonight, because the answer, and I'll whisper just the shape of it now and let it grow as we go, and the answer is that those missing atoms were never inside the galaxies at all. They never belonged to the bright islands. They were out there the whole time, in the dark between, in the spaces we'd written off as empty. The old island universe picture, you see, had quietly led us astray. It taught us to look for the matter where the light was, to assume that if you wanted to find the stuff, you went to the bright places, keeping the stars, the galaxies, the glowing clusters. That's where the action was, surely. That's where everything was gathered up. And the dark between was just the stage, the empty backdrop, the void. But the matter wasn't following our tidy picture. A great deal of it More than half had never gathered into the bright islands at all. It had stayed out in the dark, spread so impossibly thin, and heated to such an impossible temperature that our telescopes simply slid right past it for decades. It wasn't hiding exactly, it was just so faint, so diffuse, so unlike anything we knew how to look for, that we kept looking straight through it without seeing a thing. It was, in the most literal sense, the most ordinary matter in the universe, hiding in the most ordinary seeming place, the empty dark, precisely because the empty dark was the last place we thought to look. And finding it, pinning it down, weighing something that gives off almost no light at all, that would take some of the cleverest detective work in all of modern astronomy. We would have to learn how to weigh the invisible, how to take the measure of a thing that doesn't shine. We'd end up timing flashes of radio waves that cross the entire universe to reach us, and watching the color drain out of distant light, and reading the faint fingerprints that thin gas leaves pressed into the afterglow of the Big Bang itself. But all of that comes later, and there's no rush. We have all the time in the world. For now, just let the mystery settle over you like a second blanket. Two witnesses agreeing on a total, a careful count that came up half empty, and half of the ordinary universe, the simple, familiar atom and element stuff that you yourself are made of, gone missing into the dark between the galaxies, into the very places we'd always called empty. It turns out the emptiness was keeping a secret. The biggest, heaviest secret in the ordinary universe. And it was hiding it the way the best secrets are always hidden. Right out in the open, in plain sight, in the one place nobody thought worth looking. So let us go and look. Slowly, softly, one mystery at a time. Let's start by solving that very first riddle I set in front of you. The box that's 1,000,000 degrees and empty all at once. Because once you understand how something can be searingly hot and almost perfectly empty in the very same breath, you'll understand exactly how half a universe could hide in the dark for 20 years, hot enough to outshine a star, and still somehow give off almost no light at all. Picture a box. A simple, ordinary box, about the size of the one your shoes came in, sitting on the floor beside your bed. Now I want you to imagine reaching into that box, out there, in the deep space between galaxies, and pulling out everything inside it. How much would you be holding? Almost nothing. A few atoms, maybe a handful, maybe a few hundred, scattered through the whole volume, drifting past each other with vast, lonely gulfs of empty space in between. To give you a sense of how thin that is, much air in your bedroom right now, the air you're breathing as you lie there, has something like 10,000 trillion molecules packed into that same shoebox of space. The gas between the galaxies has a few. You could fit the entire population of a city's worth of those particles into a region larger than our solar system, and it would still feel, by every measure we know, like the most perfect emptiness imaginable. And yet, and here is the part that makes no sense, the part I want you to carry with you tonight, that almost nothing is glowing at 1,000,000 degrees, hotter than the surface of the sun, hotter than the heart of a furnace, a box of near-perfect vacuum, blazing at a temperature that would vaporize anything you tried to lower into it, and somehow holding both of those truths at once, calmly, the way a sleeping person holds a dream. I promise we'll untangle exactly how that's possible. There's a beautiful little trick hidden in the word temperature, and once you see it, the whole impossible thing clicks into place like a key turning in a lock. But not yet. For now, just let it sit there in your mind, unresolved and strange. 1,000,000 degrees and almost empty, the hottest, emptiest place you could ever imagine. That single picture is the doorway into everything else we're going to wander through tonight. And before we step through it, if you're enjoying this, if a calm voice and a strange idea is the kind of thing that helps you drift off, it would mean the world to me if you'd leave a like and maybe subscribe. This is a small, sleepy little channel, and small creators like me really do lean on that quiet bit of support to keep the lamps lit. So thank you truly if you do. And to those of you already here, already part of this, thank you for coming back. I'm curious too. Where in the world are you listening from tonight? A bedroom, a sofa, a long train rolling through the dark? What time is it in your corner of the world right now? Tell me if you like. I always love knowing who's out there in the quiet with me. Now, settle back in. Loosen your shoulders. There's nothing here you need to hold on to, nothing you have to understand, no test at the end. If your eyes are getting heavy, let them. If you fall asleep before we reach the answer, that's perfectly all right. The universe has been keeping this secret for billions of years, and it will happily keep it a little longer for you. The ideas will still be here tomorrow night. We're going to take this slowly. We're going to take it gently, one mystery at a time, with all the time in the world to get there. So let me take you back, not in space for a moment, but in the way we used to picture all of this. For a very long time, and honestly, it's still the picture most of us carry without ever questioning it. People imagined the universe as a great dark ocean with bright little islands floating in it. The galaxies were the islands, glittering, self-contained, full of stars and warmth and light. And between them, nothing. True nothing. The void, empty black sea stretching on forever, separating one shining island from the next. Astronomers even had a lovely old phrase for it back in the early days of the last century, when they first began to grasp that those faint smudges in their telescopes were entire other galaxies, unthinkably far away. They called them island universes, each galaxy a world unto itself, drifting alone with absolute emptiness lapping at its shores. It's a gorgeous picture, it's intuitive, it feels right. You look up at the night sky and you see the bright points and the black gaps, and your mind does exactly what minds do. It decides the bright bits are the things and the dark bits are the absence of things, the stuff and the space the stuff floats in, the islands and the sea, and it's wrong. Not wrong in some small, fussy, technical way, wrong at its very heart, backwards even, because the sea, it turns out, is where almost everything lives. The islands are the rounding error, but we'll get to that. Let it stand for now, this tidy old picture, because we're about to watch it come apart. And there's a particular pleasure in watching a thing you were so sure of gently fall to pieces, isn't there? The cracks in it began to show in a place you might not expect, not in a telescope pointed out at the dark between galaxies. They showed up in the books, in the accounting, in the simple, stubborn act of adding things up. Here is the situation. We have, it turns out, two completely independent ways of counting how much ordinary matter the universe is supposed to contain. And by ordinary matter, I mean exactly what it sounds like. The normal stuff, the atoms, protons and neutrons, the particles that make up everything you've ever touched, your hands, this bed, the water in your glass, the stars overhead. Scientists have a slightly stiff technical name for it. They call it baryonic matter, baryons. But you can just think of it as the familiar stuff, the atom and element stuff, the stuff you yourself are made of, right down to your fingertips. Now, the first way of counting it reaches all the way back to the beginning. In the first few minutes after the Big Bang, when the entire universe was a searing, dense fog hotter than the inside of any star, the very first elements were forged: hydrogen, helium, a whisper of lithium, and the exact recipe, how much of each, in what proportions, depends with exquisite sensitivity on precisely how much ordinary matter there was to work with. The physics is beautifully tight. Tell me how much hydrogen and helium came out of that first furnace, and I can tell you with real confidence how much baryonic matter the universe started with. This is called Big Bang nucleosynthesis, a fancy name for a simple idea. The universe's first 3 minutes of cooking and the recipe it left behind. That's the first witness. And here's the second. Long after that first furnace cooled, when the universe was around 400,000 years old, it had calmed enough for light to finally travel freely for the first time. That ancient light is still washing over us right now, stretched and faded into a faint microwave glow that fills the entire sky in every direction. We call it the cosmic microwave background, the afterglow of the Big Bang, the oldest light there is. And printed into the tiny ripples and patterns of that ancient glow is, once again, a precise record of how much ordinary matter the universe contained. A spacecraft called the Planck satellite mapped that faint glow across the whole sky in extraordinary detail, and from those patterns read out the recipe a second time. So now we have two witnesses, two utterly different methods. One from the universe's first 3 minutes, one from when it was 400,000 years old, looking at completely different evidence, separated by everything. And they agree. They shake hands. They both say the same thing. Ordinary matter, the atom stuff, makes up about 5% of everything. Now you might pause at that. Only 5%? What's the rest? And you'd be right to ask. The honest answer is that the overwhelming majority of the universe, the other 95%, is made of two genuinely mysterious things we call dark matter and dark energy, and we understand them so poorly that they're among the biggest open questions in all of science. But here is the thing I want to be very clear about, because it's the easiest place in this whole story to take a wrong turn in the dark. Tonight is not about that mysterious 95%. Set it aside. Let it go. We are not chasing the great unknown here. We are chasing something stranger and, in a way, more embarrassing, because our story is about the ordinary 5%, the part we thought we understood, the simple, familiar atoms we were certain we had a handle on. And that 5%, that small, well-behaved, supposedly solved sliver of the universe, was itself only half there. Because once the two witnesses had set the total, once the recipe was fixed and agreed upon, astronomers did the most natural thing in the world. They went looking. They set out to find that 5%, to point their telescopes at the universe and add up all the ordinary matter they could actually see and check it against the books. Count the stars, weigh the galaxies, tally the great clouds of gas, the glowing nebulae, the cold hydrogen drifting in the spaces between the stars, every scrap of normal matter they could lay their instruments on, all across the nearby universe, carefully summed. And the total came up wrong. Not a little wrong, not a rounding error you could shrug off. They added up everything they could find, every star in every galaxy, all the visible gas, the lot, and they came up with only about half. Somewhere between a third and a half of all the ordinary matter the universe is supposed to contain simply wasn't there. Or rather, it wasn't anywhere they could see. The recipe demanded a certain amount of atoms. The visible cosmos, counted star by star and galaxy by galaxy, could only account for half of them. The rest were unaccounted for, missing, gone from the ledger. This became one of the genuine scandals of modern cosmology, and they gave it a name as plain as the problem itself. They called it the missing baryon problem. And sit with how strange that is for a moment. We're not talking about the exotic, mysterious, dark stuff nobody understands. We're talking about plain, ordinary atoms, the same kind in your bones and your blood and the air in your lungs. and we had simply lost track of half of them. We knew with 2 independent witnesses exactly how many there were supposed to be, and we could only find 1 in 2. So where did they go? That was the question sitting on the table, heavy and unresolved, as the missing baryon problem settled into the literature, and the astronomers began to argue. Where were the atoms? Not the dark matter. Let's forget dark matter for a moment. We are not talking about that mysterious 27%, that ghostly scaffolding that barely interacts with anything. We are talking about the ordinary 5%. The bread and butter matter, the atoms, the protons and neutrons that make up everything you have ever touched or tasted or breathed. Half of them were unaccounted for in the nearby universe, and the question of where they were hiding was one of the most embarrassing open problems in cosmology for a very long time. The first instinct, the natural, reasonable instinct, was to look harder at the places already known. Maybe we had undercounted stars in faint dwarf galaxies. Maybe there was cold gas in clouds too diffuse to detect easily. Maybe the intergalactic medium, that vast space between the galaxies, held some fraction in a form just below the threshold of what the instruments could see. And astronomers did look harder, and they did find some gas that had been missed before, lurking in the circumgalactic medium. The enormous halo of gas that surrounds every galaxy like a diffuse, invisible atmosphere, far larger than the galaxy's visible disk. That helped a little. But it didn't close the gap. The books still didn't balance. The missing baryons remained missing. And then someone asked a different kind of question. Not where are the atoms hiding? But what if they are hiding in plain sight, in a form we hadn't thought to look for carefully enough? What if the answer is not that the atoms are invisible because they are too cold and dark and neutral? What if they are invisible because they are too hot? That shift in thinking is where the story gets genuinely strange, and to understand it, you need to sit with a paradox for a moment, a beautiful, counterintuitive paradox that sits at the heart of what the intergalactic medium actually is. Here it is, stated as simply as possible. The gas between the galaxies, the stuff that holds the missing baryons, is heated to somewhere between 100,000 and 10 million Kelvin. That is the range. On the cool end of it, 100,000 Kelvin is already more than 17 times hotter than the surface of the Sun, which sits at a comparatively modest 6,000 Kelvin. On the hot end, 10 million Kelvin, 10 million. Numbers like that usually belong to the cores of stars, to the interiors of nuclear reactors, to the early universe itself. And yet this gas, this supposedly empty space between the galaxies, is sitting at temperatures like that, spread across millions and millions of light years. You might be thinking, if that is true, why don't we feel it? Why doesn't all that heat pour into the galaxy, roast everything in its path, show up as some tremendous incandescence blazing across the sky? And the answer to that requires us to separate two things we tend to think of as the same, but which are, in this context, very different: temperature and heat. We use these words almost interchangeably in ordinary life, and for good reason. In ordinary life, they go together. A hot cup of tea is high temperature, and it has a lot of thermal energy to give you, but temperature and heat are not the same thing. Temperature, at the level of physics, is a measure of how fast individual particles are moving. It is the average kinetic energy per particle. A gas is hot, in the physicist's sense, when its particles are moving very, very fast. And a gas has a lot of thermal energy and has a lot of heat to give when it has both fast-moving particles and a lot of those particles. Both things have to be true for the gas to actually warm something up in any meaningful way. Now think about the intergalactic medium. The particles are moving extraordinarily fast. That is the million-degree temperature that is real, that is a genuine measurement of the per-particle speed. But there are almost no particles. The density of this gas is so extraordinarily low that you are talking about, depending on where in the intergalactic medium you are, somewhere between a few particles and a few hundred particles per cubic meter. A cubic meter. Imagine a cube roughly the size of a large wardrobe. In the densest regions of the warm-hot intergalactic medium, you might find a few hundred protons and electrons in that whole wardrobe-sized box. In the more typical regions, just a few. Compare that to the air in your room right now. The air you are breathing, the air you have been breathing your whole life without thinking about it. At sea level, there are roughly 10 to the power of 25 molecules per cubic meter. That is a 1 followed by 25 zeros. 10 million, billion molecules per cubic meter, more or less. That is normal air. That is what density feels like in ordinary life. The intergalactic medium has a few particles per cubic meter. The ratio between ordinary air and the warm-hot intergalactic medium is so extreme that it is almost impossible to write it in an intuitive way. It is the difference between a crowd and a single grain of rice on a football pitch. No, it is more than that. Far more. If you scaled it to something human, you would run out of analogies before you ran out of orders of magnitude. And here is the thing about that density, or rather, that near total absence of density. There is no vacuum chamber on Earth, not in any laboratory, not in any particle accelerator, not in any ultra-high vacuum system built by human hands, that even comes close to that emptiness. The best vacuums we can create in the lab still have millions of molecules per cubic meter. We are nowhere near the intergalactic medium. In terms of emptiness, in terms of raw particle density, the warm-hot intergalactic medium is the best vacuum in the known universe, the emptiest thing that exists. And yet it is 1,000,000 degrees. Both of those things are true simultaneously. The same gas, the same medium, the same stuff. 1,000,000 degrees, a better vacuum than anything on Earth. The temperature density paradox is not a contradiction, it is a feature of what temperature actually means at the physics level. But it is deeply counterintuitive, and it deserves to be held for a moment before we move on. Because it is the heart of the whole story. The space between the galaxies is not empty in the way you imagine, because what is there is hot. And it is not warm in the way you might expect, because there is almost nothing there to carry that warmth. Both truths at once. If you were somehow transported to the middle of the warm, hot intergalactic medium, if you could exist there without any spacesuit or protection, just you and the gas, you would not feel warmth. You would feel cold. You would feel the cold of near absolute zero, because so few particles would strike your skin in any given moment that almost no heat would transfer to you at all. A single particle hitting your skin might be moving at extraordinary speed, carrying enormous kinetic energy for its size, but there would barely be any of them. The thermal energy available in any human-sized region is negligible. You would feel nothing. The universe's hottest gas would register as the universe's emptiest cold. This is the first thing to carry forward as we try to understand the warm, hot, intergalactic medium, or the WIM as astronomers call it. And the name fits beautifully because it does have a kind of whimsical improbability to it. A thin, hot, nearly empty ghost of gas strung between the galaxies. That is the WIM. And the question of how it got that way is where the story gets richer still. Picture the universe a few billion years after the Big Bang. The cosmos is already old enough that the first great structures have begun to form. The first galaxy clusters are pulling together. The first filaments of what will become the cosmic web are condensing out of the initial nearly uniform distribution of matter. Gas at this point is still mostly the lightest stuff, hydrogen and helium, the products of Big Bang nucleosynthesis filling the universe roughly uniformly, but beginning to be tugged by gravity toward regions where matter is clumping. It flows, it falls. Gravity pulls it along the growing threads of the web, channeling it toward the intersections where clusters and galaxies will one day sit. And as it falls, as any gas falls into a gravitational well, it accelerates, it picks up speed, and then when it slams into the denser material already collecting in the filaments and around the growing clusters, it collides. When infalling gas hits a denser region and stops suddenly, the kinetic energy of that infall has to go somewhere. It cannot simply disappear. And where it goes is into heat. The gas is shock heated, that is the physicist's term for this. Heated at the accretion shocks that form where fast-moving, infalling material meets the denser medium it is falling into. The faster the infall, the greater the heating, and on cosmic scales, with gas falling toward massive structures under the pull of enormous gravitational fields over millions and billions of years, the shock heating can be extreme. Temperatures in the filaments rise, temperatures around the clusters rise more, and temperatures in the intracluster medium, the gas between galaxies within rich clusters, can rise to tens and even hundreds of millions of Kelvin, hot enough to glow brightly in X-rays. That is the first source of the WIMP's heat. Pure gravitational energy converted into thermal energy at accretion shocks as the cosmic web assembles itself. The universe is building its skeleton, and the gas caught in the construction is being heated by the process itself. It is not mysterious, it is just physics. The same physics that heats a meteor falling through the atmosphere, the same physics that makes a bicycle pump warm when you compress the air inside. Falling matter gets hot when it stops. On cosmic scales, the falling is enormous and the stopping is violent and the heat is measured in millions of Kelvin. But gravity alone cannot account for all of it. There is a second source of heat in the intergalactic medium, and it is one that tells us something important about the relationship between galaxies and the space around them. It is called feedback, and it comes from the galaxies themselves. Think about what happens inside a galaxy. Stars are born and they live and they die, and when the most massive of them die, when they exhaust their nuclear fuel and collapse in on themselves, they explode as supernovae. A supernova is not just a local event. It does not just rearrange the dust near the dying star. It releases energy on a scale that can drive enormous winds of gas outward from the galaxy, sweeping material into the surrounding medium. Individually, one supernova is tiny on cosmological scales, but galaxies have had billions of years and billions of stars, and the collective effect of countless supernovae driving gas outward, enriching and heating the gas beyond the galaxy's visible boundaries, is substantial. It adds heat to the circumgalactic medium and, over time, to the intergalactic medium beyond it. And then there are the black holes, not ordinary stellar mass black holes. We are talking about the supermassive black holes that sit at the centers of many galaxies, including our own. When these objects are actively feeding, when gas is falling into them and forming accretion disks and launching jets, the energy they release is staggering. An actively feeding supermassive black hole, what astronomers call an active galactic nucleus, or AGN, can release more energy than the rest of the entire galaxy combined. Much of that energy goes into heating and driving gas. And not just the gas inside the galaxy, but the gas surrounding it. AGN feedback is now understood to be one of the primary mechanisms by which galaxies regulate their own star formation by driving gas outward into the circumgalactic medium and beyond, preventing too much material from falling back in and forming stars too quickly. The consequence for the intergalactic medium is direct. All of that AGN-driven gas, heated, pressured, launched outward at tremendous velocities, travels beyond the galaxy's visible disk and eventually mingles with the intergalactic gas in the filaments and the voids. It adds more heat, it adds more pressure, And it adds something else, something that tells an even more remarkable story about what the intergalactic medium actually is. The gas between the galaxies is not pristine. It is not the pure, untouched hydrogen and helium that emerged from the Big Bang and simply spread through the cosmos undisturbed. That would make a certain kind of intuitive sense. After all, if nothing has been happening out there between the galaxies, the original Big Bang composition should be preserved, right? But that is not what we find. The intergalactic medium contains metals. That word metals has a specific meaning in astronomy that differs slightly from everyday usage. To an astronomer, metals means everything heavier than helium: oxygen, carbon, neon, iron, nitrogen, silicon. All of it falls under the heading of metals in the astronomical sense. And there is a crucial thing to understand about metals in this context. The Big Bang did not make them. The Big Bang produced hydrogen and helium and a little lithium. That was it. Every single atom heavier than helium, every atom of oxygen, every atom of carbon, every atom of iron was forged inside a star. Stars are the universe's element factories, burning lighter elements into heavier ones through nuclear fusion in their cores, and then, when they die, releasing those heavier elements into space through stellar winds and, most dramatically, through supernova explosions. This means that metals, in the astronomical sense, are an unmistakable signature of stellar processing. Find metals somewhere, and you know that somewhere, at some point, stars lived and died and sent their ashes outward. No exceptions, no other mechanism. Stars made the metals, and the metals carry the proof of where they came from. Now look at the intergalactic medium. Look at the gas strung between the galaxies, out in the filaments and the diffuse regions between the great clusters and walls of the cosmic web. And find in that gas oxygen. Find carbon, find neon, find iron, all of them there, far from any visible galaxy, spread through the supposedly empty intergalactic medium. The only possible explanation is that these atoms were forged inside galaxies, and then blown outward, beyond the galaxy's visible edge, beyond its circumgalactic medium, out into intergalactic space. The metals in the intergalactic medium are, in the most literal sense, the exhaust of the galaxies. The processed material, the ashes of dead stars, pushed out by supernovae and AGN winds, and the collective pressure of galactic activity over billions of years until it mingles with the gas of the cosmic web. The intergalactic medium is not separate from the galaxies. It is, in part, made of them. It is partly galactic exhaust spread thin across the enormous distances between the islands of stars, telling us that the boundary between a galaxy and the space around it is not clean or sharp, but is instead a porous, active, dynamic exchange. Galaxies breathe matter outward. The intergalactic medium carries the evidence of that breathing in its chemical composition, and this is where the detection story begins to get specific and wonderful. Because detecting metals in the intergalactic medium, detecting the warm hot gas where the missing baryons live, is not simple. The WIM does not glow the way stars glow. It does not emit the kind of visible light that you can just point a telescope at and photograph. It is too diffuse, too thin, spread over too enormous a volume. So how do you find it? How do you prove it is there? How do you weigh something that doesn't shine? One answer comes from oxygen, specifically from oxygen that has been stripped almost completely of its electrons by the tremendous heat of the WIM. A neutral oxygen atom has 8 electrons, but in the million-degree gas of the warm-hot intergalactic medium, collisions between particles are so energetic that electrons are knocked away, ionized off the atoms. 7 times ionized oxygen would have only 1 electron left. 6 times ionized oxygen, called O7, has had 6 of its 8 electrons stripped away, leaving just 2. At the temperatures of the WIM, this is exactly what you would expect to find. Highly ionized oxygen, including O7 and the slightly cooler O6, missing 5 electrons, is a direct tracer of gas at WIM temperatures, and you can detect it not by seeing it shine, but by watching what it does to light passing through it. When a very distant, very bright object, a quasar, shines its light across billions of light years, that light passes through everything in its path. And when it passes through a region of gas containing O7 or O6, those highly ionized oxygen atoms absorb light at very specific wavelengths. Particular colors, particular energies of photon, are swallowed by the O7 ions and subtracted from the quasar's spectrum. When the light arrives at our telescopes, it has been imprinted. Little notches have been carved into the spectrum at the exact frequencies that correspond to O7 and O6 absorption. And those notches tell us, with remarkable specificity, not only that the gas is there, but also what temperature it is at, what phase of ionization it is in, and therefore how much of it there might be. This is the technique that Fabrizio Nicastro and his colleagues used in 2018 in a paper that landed in the journal Nature, and which represented one of the most significant steps towards solving the missing baryon problem. The target was a distant quasar known somewhat prosaically as 1ES 1553+1 Its light, on the billions of years' journey from the quasar to our telescopes, passes through the cosmic web, through the filaments and the diffuse regions of the intergalactic medium. And in that light, Nicastro's team found the fingerprints of O7, 2 absorption lines at the right wavelengths consistent with the expected WIM temperatures found in X-ray observations of the quasar's spectrum. The highly ionized oxygen was there, in the intergalactic medium between us and the distant quasar, and the amount of gas that absorption implied was consistent with the WIM holding a significant fraction, potentially all, of the missing baryons. Pause on what that detection required for a moment. You are looking at a single object, a quasar billions of light years away. The light from that quasar is ancient. It left its source long before our solar system existed. On its journey here, it has been passing through the cosmic web, through filaments of gas containing atoms of oxygen that were once forged in the hearts of stars that lived and died in galaxies millions of light years from the quasar's path. Those oxygen atoms, stripped of 6 of their electrons by the surrounding heat, absorbed specific wavelengths of the quasar's X-ray light so faint and subtle that detecting them required the sensitivity of space-based X-ray telescopes and painstaking analysis of the resulting spectrum. And from that, from a pair of tiny absorption features in the light of a distant point source, you can prove that the gas is there and roughly how much of it exists. It is detective work of the most extraordinary kind. The universe does not hand you the evidence on a silver platter, you read it in the shadows. But oxygen absorption in quasar spectra, as remarkable as it is, can only sample the WIM along specific lines of sight, the narrow pencil beams of light from individual quasars. To build a fuller picture of the missing baryons spread across the cosmos, you need a different approach, and one of the most elegant came from something completely different, from radio bursts lasting milliseconds, born in some of the most dramatic events in the universe, fast radio bursts, FRBs. These are extraordinarily brief flashes of radio waves, lasting anywhere from a fraction of a millisecond to a few milliseconds, originating from cosmological distances. They were only first discovered in 2007, and for years afterward their origin was uncertain and their nature debated. But regardless of their source, and we now believe most FRBs come from magnetars, neutron stars with extraordinarily powerful magnetic fields, undergoing sudden, energetic events. What matters for our story is what happens to their signal on the long journey to our telescopes. Radio waves do not all travel through space at exactly the same speed. In a perfect vacuum they do. The speed of light is the speed of light. But in a medium containing free electrons, and the intergalactic medium, even as diffuse as it is, does contain free electrons. Different frequencies of radio waves are slowed by slightly different amounts. The lower the frequency, the more the wave is slowed by interacting with the free electrons it passes through. So a radio burst that sets off from its source with all its frequencies arriving simultaneously will, by the time it reaches Earth, have been smeared out in time. The high-frequency end arriving first, the low-frequency end arriving a tiny fraction of a second later. The burst arrives as a sweep, a chirp, from high to low. The size of that smearing, at what astronomers call the dispersion measure, is a direct, quantitative measure of the total number of free electrons the burst passed through on its journey, and free electrons in the intergalactic medium come from atoms. From the baryons, the ordinary matter spread through the cosmos. So the dispersion measure of an FRB is, in a very direct sense, a measure of how much ordinary matter lies between us and the source. In 2020, J.P. Marquardt and his colleagues, using the Australian Square Kilometre Array Pathfinder, ASCAP, published a landmark result. They had measured the dispersion measures of multiple FRBs at known cosmological distances, and what they found confirmed something that had been predicted theoretically, but never before directly measured. The dispersion measures of distant FRBs were systematically higher than those of nearby FRBs in proportion to their distance. This relationship, now called the Marquardt relation, in honor of J.P. Marquardt, who died not long after the paper was published, directly measures the average density of baryons in the intergalactic medium. And what the Marquardt relation gave them was the full census. The FRB dispersion measures were consistent with the baryons predicted by the cosmic microwave background and by Big Bang nucleosynthesis. The full complement of ordinary atoms was there, spread diffusely through the cosmos between the galaxies in the intergalactic medium. The missing baryons had been found, not in new places that required exotic physics, not in some overlooked population of galaxies. They were out there, in the thin gas between the galaxies, in the filaments and diffuse regions of the cosmic web, dispersing radio flashes from magnetars and imprinting their shadows on the light of ancient quasars. And there is still another method, a third, independent line of evidence that tells the same story from a completely different direction. This one involves not quasar light or radio bursts, but the oldest light in the universe, the cosmic microwave background, the afterglow of the Big Bang itself, that faint wash of microwave radiation that fills the sky in every direction, the last light emitted when the universe was only about 380,000 years old, and finally cool enough for electrons to combine with protons and form neutral hydrogen. The CMB has been traveling ever since, for nearly 14 billion years, a relic of the epoch when the universe became transparent. And on its journey to our telescopes it passes through everything, including the gas in the intergalactic medium. When CMB photons pass through a region of gas where electrons are moving, and in the warm, hot intergalactic medium, the electrons are definitely moving at million-degree velocities. Those photons can be scattered. They collide with the fast-moving electrons and exchange a tiny amount of energy. This changes the spectrum of the CMB photons ever so slightly. And if the electrons in the region are not just hot but moving collectively, moving in bulk the way gas in a filament might be collectively flowing in some direction, then this scattering produces a distinctive signal. The CMB photons passing through the moving gas are distorted in a particular way, slightly more energetic on the side the gas is moving toward, and slightly less energetic on the opposite side. This effect is called the kinetic Sunyaev-Zeldovich effect, or KSZ. It is tiny. The The distortions are at the level of millionths of a degree. But they are real, and they are detectable with sensitive enough instruments. In 2017 and 2018, two independent teams used the KSC effect to do something remarkable. Rather than trying to detect the distortion from one filament, which would be too faint to see, they stacked thousands of signals from pairs of galaxies, lining up the direction of the filament connecting each pair and averaging the CMB distortions from many such pairs simultaneously. The stacked signal, pulled out of the noise by the combination of thousands of measurements, revealed gas between the galaxy pairs, gas moving in the filaments, gas consistent in density with the missing baryons. Three independent lines of evidence: oxygen absorption in quasar spectra, fast radio burst dispersion measures, the kinetic Sunyaev-Zeldovich effect in the CMB. All pointing to the same answer, all finding baryons in the intergalactic medium, all consistent with the idea that the missing half of the universe's ordinary matter had been lurking between the galaxies all along, in a thin, extraordinarily hot, almost perfect vacuum that had simply been difficult to see by conventional means. And then there is the Lyman alpha forest, which tells the same story, but from a cooler, denser edge of the intergalactic medium, and which gives one of the most visually striking ways to picture what it means for the space between galaxies to be full of gas rather than empty. A quasar shines. Its light begins a journey that will take billions of years. It sets off through the universe, and between the quasar and us, there are not nothing, not a clean, empty void, but thousands upon thousands of clouds and filaments of hydrogen gas at varying densities and temperatures. Some of them are cool and relatively dense, some are part of the cosmic web's filaments, some are the tenuous threads of the diffuse intergalactic medium. Each one, as the quasar's ultraviolet light passes through, absorbs some of it. Hydrogen has a very specific wavelength at which it likes to absorb light, the Lyman alpha line at 121 nanometers, and every cloud the light passes through removes a little of the quasar's light at that wavelength, but shifted by the expansion of the universe, redshifted, to a slightly longer wavelength depending on how far away the cloud is. By the time the light reaches our telescopes, the quasar's spectrum has been carved up, not by one absorption feature, but by hundreds, thousands. Each cloud, each filament, each wisp of intergalactic hydrogen has left its mark. The result, when you plot the quasar's spectrum, looks like a dense forest of absorption lines, each one a different distance, a different cloud, a different whisper of gas the ancient light passed through on its billions of years journey. Astronomers call this the Lyman alpha forest, and it is one of the richest sources of information about the structure of the intergalactic medium across cosmic history. A single quasar's spectrum containing the Lyman alpha forest is a map. Not a map of what the quasar itself is like, but a map of everything the quasar's light passed through. Every line in the forest is a place. Every absorption feature is a cloud, a filament, a structure in the cosmic web that the light traversed on its way to us. It is as if you could determine the composition of every room in a long corridor simply by analyzing what a lamp at the far end of the corridor looked like by the time its light reached you at the other end. The lamp's light tells you about the intervening rooms, not about the lamp itself. And the Lyman alpha forest tells us that the space between the galaxies is full, not empty, not void, full, not densely full, not rich with stars and planets and complex chemistry, but full of gas, full of the thin, diffuse, occasionally hot, occasionally cooler medium that fills the filaments and sheets and diffuse regions of the cosmic web. The missing baryons are not a mystery anymore. They are in that gas, in that forest of absorption lines, in the dispersion of fast radio bursts, in the shadows cast on quasar light by 6 times ionized oxygen, in the kinetic distortions written into the oldest light in the universe. They are there. all of them accounted for at last, after decades of being unaccounted for. And sit with this for a moment, because it is the turn in the story. The revelation that the missing baryon problem has solved itself, not by finding atoms in unexpected places, but by realizing that the expected places were wrong. The astronomers had been looking in the galaxies. Of course they had. Galaxies are bright. Galaxies are where the stars are. If you are looking for matter, you look where the light is. But most of the matter, most of the ordinary matter, the bread and butter atoms, the baryons the universe made and that the CMB ledger demands, is not in the galaxies at all. Estimates of the partition are still being refined, and different detection methods sample different phases of the gas and don't all agree perfectly on the precise breakdown. But the headline is clear and supported by multiple lines of evidence. Somewhere between 50 and 90% of all the ordinary matter in the universe today lives outside galaxies, in the intergalactic medium, in the WIM, in the cooler diffuse IgM, in the circumgalactic halos surrounding galaxies, in the intracluster gas within galaxy clusters. The exact numbers are live science. The direction of the answer is not. Stars. The shining, visible stars that we see in photographs of galaxies, the stars that make galaxies look bright and beautiful and substantial, contain only about 7 to 10% of all the baryons in the universe. Not 7 to 10% of the exotic dark matter, not 7 to 10% of the mysterious dark energy that dominates the cosmos. 7 to 10% of even the ordinary matter. The shining part, the part that makes the night sky look the way it does, is a rounding error in the baryon budget, a thin silver dusting on the surface of a vastly larger ocean of invisible gas. The galaxies, in other words, are the foam. The intergalactic medium is the ocean, the bright islands of stars and gas and dust that we call galaxies, the things that for centuries astronomers thought of as the main event, as the fundamental structures of the cosmos, the island universes floating in void, are in the baryon budget a minority. They are where matter has condensed and collapsed and lit up. But they are not where most of the matter is. Most of the matter is spread between them, thin and hot and dark to the eye, waiting to be found by clever instruments and patient analysis, and a willingness to look for what is not shining rather than what is. That is the inversion the dossier promised, and here it is, plainly stated, not as a metaphor, not as a poetic gesture toward the unknowable, as a fact supported by 3 independent detection methods consistent with the bookkeeping of the Big Bang. The galaxies are the foam, the ocean is what lies between them, and the ocean is hot. And the ocean contains the ashes of stars, the metals, the oxygen and carbon and iron forged in stellar cores and blown outward by the deaths of those stars, spread thin across millions and millions of light years. The intergalactic medium is not separate from the story of stars and galaxies. It is the receiving medium for their exhaust, for the material they have spent billions of years processing and ejecting. It connects them. It is partly made of them. You are lying where you are right now, made of atoms. Carbon atoms. Oxygen atoms. Atoms that were forged inside stars that lived and died long before our sun was born. That much perhaps you have heard before. But here is the part that is less often said. Some of the atoms that will eventually build the next generation of stars, and the atoms that are, right now, between the galaxies, dissolved in the warm, hot, intergalactic medium at temperatures of hundreds of thousands to millions of Kelvin, moving so fast that they have shed most of their electrons. Some of those atoms were once inside galaxies like ours. They were forged in stellar cores, ejected by supernovae, blown outward by AGN winds, dispersed into the circumgalactic medium, and then pushed further still into the intergalactic void, where they have been drifting hot and thin for billions of years. The intergalactic medium is not just what lies between the galaxies, it is also what the galaxies have given back to the universe, and someday, in the deep future, some of that material may fall back in, may cool and condense along the filaments of the cosmic web and trickle back toward galaxies old and new, to be forged again into stars, into planets, perhaps into something that wonders about it all. But we are getting ahead of ourselves because we have been talking about the gas, the hot, thin, metal-enriched gas that fills the intergalactic medium. And we have not yet properly talked about the architecture, the structure, the framework that organizes the gas into filaments and walls and voids and knots. We have mentioned the cosmic web in passing, but we have not yet stood inside it and looked around. And that is where the story goes next. So, the gas is there. We have established that much. The warm, hot intergalactic medium hangs between the galaxies, thin as a whisper, burning at temperatures that would vaporize any material thing we have ever made, and yet so sparse that a cubic meter of it holds only a few atoms, rattling around in what amounts to the finest vacuum in nature. We know what it is. We know, in broad strokes, where it sits and why it runs so hot. But knowing something and proving it are two entirely different things. And for decades, the proof was the problem, because here is what astronomers were left with once the theoretical picture had been drawn out and the simulations had confirmed it, and the reasoning all pointed the same direction. They had a ledger, the careful accounting of the universe's ordinary matter, written in the light of the cosmic microwave background, and in the ratios of hydrogen and helium and lithium that came out of the Big Bang's first minutes. That ledger was precise. It said, this is how many baryons exist. This is how much ordinary matter was created. And when they went looking for all of it, counting up every star, every galaxy, every cloud of gas they could see, they came up short. Roughly half of it was simply missing, not hiding in dark matter. That is a different story entirely, and not the one we are telling tonight, just ordinary atoms made of protons and neutrons, the same stuff your body is made of, the same stuff the stars are made of, roughly half of them nowhere to be found. The warm, hot intergalactic medium was the leading suspect. The simulations pointed to it, the physics said the gas should be there, but for a long time, the WIM was a theoretical object, something that had to be inferred rather than seen, something astronomers believed in the way you might believe a room is occupied because you can hear breathing through the door without having opened it yet. The problem is not a small one. If you want to detect something, you generally need it to glow. You need photons, light, traveling from the object to your telescope. And the WIM, for all its ferocious temperature, is desperately bad at producing light you can easily collect. It is too hot for ordinary hydrogen emission. It is too diffuse to produce much of anything. The very properties that make it the dominant reservoir of ordinary matter, its thinness, its spread across hundreds of millions of light years, are the same properties that make it nearly invisible. So how do you weigh something that doesn't shine? That question sat at the heart of observational cosmology for decades, and the answers, when they came, were extraordinary. Not because they used bigger and bigger telescopes to see fainter and fainter things, though that was part of it, but because they used the universe itself as the instrument. They found ways to read the gas, not by looking at it directly, but by watching what it did to the light of other things passing through it. Let's start with the most dramatic of these methods, the one that involves milliseconds, a radio dish in the Australian desert, and flashes of light so brief they are over before you have finished a single blink, fast radio bursts. If you have not encountered them before, they are exactly what their name suggests: short, intense bursts of radio waves arriving from somewhere very far away, lasting only a few milliseconds at most, and then gone. The first one was discovered in archival data in 2007 by astronomer Duncan Lorimer, which is why the original class were called Lorimer bursts for a while. And they confused everyone immediately because they were too brief to study, too variable to predict, and too bright to be local. Whatever was making them had to be producing enormous energy. In a few milliseconds, a single fast radio burst releases as much energy as the sun emits over days or weeks or even months, depending on the burst. What makes them are still being worked out. Magnetars, neutron stars with almost incomprehensibly intense magnetic fields, are the leading explanation, and there is now quite good evidence pointing that way. But for tonight's purposes, what matters is not what makes them. What matters is what they do on their journey to us. When a fast radio burst is created somewhere out there, maybe billions of light years away, it sets off across the cosmos at the speed of light. And as it travels, it passes through gas. The diffuse, thin, largely invisible gas of the intergalactic medium. And that gas does something to the burst that acts as a kind of fingerprint. Here is the thing about radio waves. Different frequencies travel through charged gas at slightly different speeds. High-frequency radio waves, the shorter ones, slip through faster. Lower-frequency radio waves, the longer ones, get slowed down a little more. Not by much, not by anything you would notice if you were crossing a room. But across billions of light years, even the tiniest difference accumulates. By the time a fast radio burst reaches us, the high-frequency part of the burst arrives first, and the lower-frequency part arrives a fraction of a second later. The burst is smeared out in time by the gas it crossed, and that smearing, that time delay between the frequencies, is measurable. It is called the dispersion measure, and it is directly proportional to the number of free electrons the burst passed through on its journey. Count the electrons and you have weighed the gas. This is breathtakingly elegant if you stop to think about it. A flash of radio waves born in a cataclysm on the other side of the universe arrives at a dish in the Australian outback, and written into the tiny delay between its frequencies is the total mass of all the diffuse gas it crossed, all the atoms dissolved into the intergalactic medium across billions of light years of cosmic web. The universe encoded the answer in the message itself. In 2020, a team of astronomers using the Australian Square Kilometre Array Pathfinder, ASCAP, a radio telescope array in Western Australia, published exactly this measurement. The lead author was J.P. McQuart, and the relationship they used to extract the baryon census from FRB dispersion measures is now called the McQuart relation in his honour. McQuart died later that year, in 2020, before fully seeing the impact of that work, and the relation bearing his name is a small but permanent memorial to it. What McQuart and his colleagues found was this: when you collect enough fast radio bursts from enough different directions across the sky, and you plot the dispersion measure against the distance to each burst, you get a relationship. And that relationship, when you do the math, tells you how much diffuse gas lies along the average line of sight through the cosmos. And the number that came out of that analysis was consistent with the full baryon budget. Not half of it, not 2/3. The full census, the number the cosmic microwave background demanded and the local count of stars and galaxies could not reach, was there, spread thinly through the intergalactic medium where the simulations had always said it would be. The missing atoms had been found. They had been found by timing radio flashes from across the universe, millisecond by millisecond. Take a moment with that if you like, no rush. Now, the ASCAP result was a census. It told you how much gas in total is out there. But a census does not always tell you where exactly or in what condition. You know the population number, you do not necessarily know the neighborhood. And for the warm-hot intergalactic medium specifically, the gas at 100,000 to 10 million Kelvin, the gas in the filaments of the cosmic web, astronomers wanted something more targeted. They wanted to catch the whim in the act, to see its fingerprint not just in a statistical smearing of radio waves, but in a specific, identifiable spectral line, a chemical signature, a color of light that only this particular gas, at this particular temperature, could produce. And for that, they looked to X-rays and to oxygen. Oxygen, you will recall, is one of the metals that the intergalactic medium carries, forged inside massive stars, scattered into space by supernovae, blown outward by galactic winds and the fury of active galactic nuclei, and then carried far beyond the galaxies themselves into the intergalactic medium. At the temperatures of the WEM, atoms lose many of their electrons. An oxygen atom has 8 electrons to begin with. Strip away 6 of them and you are left with what astronomers call O7, oxygen in the 7th ionization state, carrying only 2 electrons instead of 8, orbiting a nucleus with 8 protons and almost nothing else to keep them company. This highly ionized oxygen absorbs X-ray photons at a very specific energy, a very precise fingerprint in the spectrum. If you have a bright enough source of X-rays shining from far away, and the light from that source passes through a filament of warm, hot, intergalactic gas on its way to your telescope, the O7 in that gas will leave a tiny absorption mark at that precise energy, a small darkening at a very specific wavelength. The light dims just a little at exactly the frequency that 6 times ionized oxygen prefers. And if you can measure that dimming, you have directly detected the hot intergalactic gas. The ideal background lighthouse for this kind of measurement is a quasar. Quasars are the luminous hearts of distant galaxies, powered by supermassive black holes consuming material at enormous rates, and they are among the brightest objects in the universe. In X-rays, some quasars shine brilliantly enough to be seen across billions of light-years. They are the perfect backlights, extraordinarily bright point sources whose spectra can be studied in detail as their light weaves through the cosmic web on its way to us. In 2018, an astronomer named Fabrizio Nicastro and his colleagues published a paper in the journal Nature reporting just such a detection. The quasar they used was designated 1ES 1550-13, a relatively compact name for one of the universe's more extraordinary objects, an active galaxy pumping out X-rays brightly enough to serve as a beacon across roughly 4 billion light-years of space. As that X-ray light traveled toward us, it passed through intervening material, including, Nicastro and his team argued, at least one filament of the warm, hot, intergalactic medium. And in the spectrum of that quasar, they found it. The absorption signature of O7, the 6 times ionized oxygen, sitting precisely where the models predicted it should be, at precisely the distance consistent with an intervening cosmic web filament. It was a delicate detection. The absorption features were faint, as you might expect from gas this diffuse, but the signal was there, and the team calculated that the amount of gas implied by those absorption lines was consistent with what the missing baryons required. They had, for the first time, directly and spectroscopically caught the whim. Caught it in absorption, caught it at the exact temperature and chemical composition the theory predicted, caught it by watching its chemical fingerprint dim the X-ray light of a distant quasar crossing the intergalactic dark. It is worth pausing here to appreciate just how refined an instrument the universe is being asked to serve as. The X-ray light from 1ES 1553+113 travels for billions of years across the cosmos. On the way, it passes through thin wisps of incredibly hot gas. Gas so thin you could travel through it for years without hitting a single atom, yet so vast in extent that it holds the majority of the universe's ordinary matter. And in that brief passage, the gas stamps its chemical signature onto the light, an almost imperceptibly faint mark that our telescopes, floating in orbit above the Earth's atmosphere, can measure. And from that mark, we read the composition and quantity of the gas. The faint dimming of ancient light tells us where the atoms went. This is what Fabrizio Nicastro and his team did. It is a very beautiful thing. Now there is a third method, and it is perhaps the most conceptually strange of all because it uses the oldest light in the universe as its instrument. You have heard about the cosmic microwave background, the faint afterglow of the Big Bang, the light that was released roughly 380,000 years after the universe began, when it had cooled enough for electrons and protons to combine into atoms for the first time, and the cosmos went from an opaque fog to a transparent space full of light. That light is still traveling. It fills the entire sky. It is the oldest photons we can detect, and when they left their source, the universe was tiny and uniform and unimaginably different from what it is today. We have mapped this background light in extraordinary detail, most recently with the Planck satellite and its structure. Its tiny variations in temperature and density tells us an enormous amount about the early universe and the composition of the cosmos. But those ancient photons do not travel through emptiness on their way to us. They travel through the same universe we are exploring tonight, through the cosmic web, through galaxy clusters, through the circumgalactic medium, and through the warm, hot, intergalactic gas that hangs between galaxies in the filaments. And as they pass through gas that is moving, gas that is being pulled towards some gravitational center or pushed outward by pressure, that motion leaves a mark on the photons. A very small mark, a tiny shift in energy, so slight that you cannot see it looking at a single pixel of the CMB map. But you can find it if you are clever about where you look. The effect is called the kinetic Sunyaev-Zeldovich effect, KSZ for short, named for the Soviet astrophysicists Rashid Sunyaev and Yakov Zeldovich, who described it theoretically in the 1970s. The physics is this: when a CMB photon passes through a gas of fast-moving electrons, those electrons can scatter the photon and shift its energy slightly. If the gas is moving toward us, the photons get a tiny boost in energy, slightly blue-shifted. If the gas is moving away, they lose a little, slightly red-shifted. The net result is a minuscule distortion in the temperature of the CMB at that point on the sky, positive or negative, depending on whether the gas is coming or going. This distortion is vanishingly small for any single patch of gas. The intergalactic medium in a single filament is simply too thin to imprint much of a signal, and here is the cleverness. If you know where to look, you can stack the signals from many filaments at once. If you take pairs of galaxies that are close enough that you expect a filament to run between them, and you stack the CMB map centered on those pairs, the tiny signals add up while the random noise averages out. In 2017 and 2018, two independent teams did exactly this. They took galaxy catalogs and CMB data, identified galaxy pairs at the right distances, stacked the CMB temperature maps between them, and found a signal, a faint excess of CMB distortion in the space between the galaxy pairs, consistent with warm gas in a filament bridging them. The gas they were seeing was not dense enough to glow brightly in any ordinary way, but it was dense enough to leave its handprint on photons that had been traveling since the universe was less than 1 million years old. Think about what that means for a moment. The afterglow of the Big Bang, light that has been traveling for nearly 14 billion years, carries right now, embedded in its faint temperature fluctuations, information about the gas that is presently sitting between the galaxies. The oldest light in the universe is the messenger for the present-day intergalactic medium. It is a beautiful collision of the ancient and the contemporary, and it worked. Between the KSZ detections in 2017 and 2018, and the FRB sensors from ASCAP in 2020, and the X-ray absorption detection in Nature from Nicastro's team in 2018, the case was assembled. 3 completely different physical mechanisms, 3 completely different observational techniques, 3 completely different telescopes and data sets, and they all pointed the same way. The gas is there. The missing baryons are in the intergalactic medium as diffuse warm-hot gas threaded through the cosmic web. The accounting scandal that had run for decades, the missing half of the ordinary universe, was solved not by a single dramatic discovery, but by a convergence, a slow accumulation of independent evidence, each piece fitting against the others until the picture was undeniable. The universe had been keeping the atoms all along. We just needed to find the right language to ask. And while we are on the subject of languages, of ways the universe writes its messages, there is one more I want to tell you about because it is perhaps the oldest technique and in some ways the most evocative. It goes by a name that sounds like something from a forest at the edge of a myth, the Lyman Alpha Forest. To understand it, you need to understand what happens to light from a very distant quasar on its long journey to our telescopes. A quasar at high redshift, one whose light has been traveling toward us for 8 or 10 or 12 billion years, is separated from us by an enormous slice of the universe. And over that distance, its light does not travel through nothing. It passes through intergalactic space which, despite being a very good vacuum, contains thin wisps of hydrogen, the dominant element, the most abundant atom in the cosmos. Most of this hydrogen in the intergalactic medium has been ionized by the ultraviolet light that fills the cosmos, much of it coming from quasars themselves. But in the cooler, slightly denser filaments, some of it remains as neutral atomic hydrogen. Neutral hydrogen has a very well-known appetite. There is a particular wavelength of ultraviolet light in the Lyman alpha transition that neutral hydrogen absorbs very efficiently. When a photon of exactly that wavelength encounters a neutral hydrogen atom, it is absorbed. It disappears from the beam. And because the universe is expanding, the light from a distant quasar is continuously being redshifted as it travels. What starts as light at one wavelength is steadily shifted to longer and longer wavelengths the further it travels. What this means is that as the quasar's light makes its multi-billion-year journey, every time it passes through a pocket of neutral hydrogen along the way, that hydrogen absorbs it at whatever the local Lyman alpha wavelength happens to be at that point in the expansion. And each absorption event leaves a dark notch in the spectrum, a missing sliver of light at a specific wavelength. Many passes through many clouds of hydrogen over many billions of years means many notches. By the time the quasar's light arrives at our telescopes, its spectrum is riddled with these absorption marks, a dense thicket of dark lines, one for every encounter with neutral hydrogen along the way. That thicket is the Lyman alpha forest, and it is dense. A single quasar spectrum can contain hundreds of these absorption lines, hundreds of encounters, each one a separate wisp of intergalactic hydrogen stamped into the ancient light as it crossed the cosmos. Each line corresponds to a particular distance, a particular epoch in the universe's history, because the redshift tells you when and where along the journey the absorption happened. You are, in effect, reading a cross-section of the universe. All the hydrogen clouds, all the filaments of the cosmic web, everything the light passed through on its billions of years journey from a blazing quasar to a spectrograph orbiting the Earth, all of it is recorded there, in the notches in the spectrum. The Lyman alpha forest does not probe the hottest part of the WIM. The million-degree gas is too ionized to produce these lines. It has been stripped of its electrons and can no longer absorb in this way. What the forest traces is the cooler, more diffuse, photoionized warm intergalactic medium. the gas that fills the moderate density filaments and the walls of the cosmic web. It is a different phase of the same broad picture, and it has been used since the 1990s to map the large-scale structure of the universe in extraordinary detail, because what the forest is, when you decode it, is a three-dimensional map of where the intergalactic hydrogen is, and therefore, by implication, where the filaments of the cosmic web run. Think of it this way: you take one quasar and you get one long transect, one line drawn through the universe, sampling the gas at hundreds of different distances along that line. Take many quasars spread across the sky and you have many transects. Cross-reference them and patterns emerge. You can see how the density of intergalactic gas varies with position. You can see the filaments as regions of higher absorption and the voids as regions of lower absorption. You are reading the web by the shadows it casts in ancient light. It is not so different in spirit from what Nicastro's team did with the quasar 1ES 1553 plus 115 and the oxygen absorption lines, except that the Lyman alpha forest does it not for one phase of gas, but for the warm, somewhat cooler intergalactic medium, and not for one quasar, but for many thousands, building up a statistical picture of the universe's gaseous skeleton. And here is something worth sitting with if you are still with me, still half awake in the dark. All of these methods, the fast radio bursts and their dispersed millisecond pulses, the X-ray spectra and their faint oxygen absorption lines, the kinetic Sunyaev-Zeldovich effect stamped into the afterglow of the Big Bang, the Lyman alpha forest of shadows in quasar light. None of them look at the intergalactic medium directly. None of them involve pointing a telescope at empty space and watching the gas glow. Every one of them is a form of reading. The universe is a text, and the gas between the galaxies writes itself into every beam of light that passes through it, and we have learned, slowly, to read what it writes. That is what makes the missing baryon problem's resolution so satisfying. It was not solved by building a bigger telescope and seeing something brighter. It was solved by developing more sensitive ears, more refined ways of reading the messages already arriving, until the signal that had always been there finally became legible. And what the messages say collectively, when you have gathered all of them and decoded each one, is this: the ordinary matter of the universe is mostly out there, in the intergalactic medium, in the warm-hot gas of the WIM and the cooler photoionized gas traced by the Lyman alpha forest and the hot intracluster gas of galaxy clusters. The stars and galaxies, for all their brilliance, are a minority. The thing that shines is not the thing that dominates. This is worth letting sink in for a moment, because it is genuinely strange. We build our intuitions about the cosmos from what we can see. Stars shine. Galaxies are the great cities of the universe, the places where the action is. When we look up and try to imagine the cosmos, we picture galaxies, spirals and ellipticals and clusters separated by dark expanses of space. The space between the galaxies is the stage, the galaxies are the players. This is the picture we carry. But the picture is inverted. The gas between the galaxies is not the stage. The gas between the galaxies is the main event. The galaxies are, and I want to be careful with this image because it is not just rhetoric. The galaxies are the foam, the bubbles on the surface of a much larger ocean. The ocean is the warm, hot, intergalactic medium, the diffuse cosmic gas, the thin million-degree material that fills the filaments and traces the web. The stars and galaxies are where some of it condensed, lit up, did its brief and glorious work, and then partially exhaled itself back out again. And the atoms that are in you right now, the oxygen you just breathed in, the carbon in every one of your cells, the iron in your blood, those atoms have spent the vast majority of their existence not inside a star or a planet or a living body. They have spent most of their existence somewhere between the galaxies as part of that thin, hot gas drifting through the dark. The time inside a star was a brief, bright episode. The time inside you is briefer still. The long, slow chapters of atomic history are written in the intergalactic medium, and the stellar chapters are the exception. But we are still not quite finished with the detective story. Because finding the gas was one thing. Understanding the full architecture in the structure that organizes the gas, the scaffolding that gives the universe its shape, that is the next chapter. The cosmic web, which we have been gesturing at throughout this journey, deserves to be more than a phrase. It deserves to be walked through. And there is still the question of the emptiness, the other side of the title's promise. The places where there really are no stars, or very nearly none. The great voids. The places where the web pulls back and leaves almost nothing. We have been talking about the gas in the filaments. We have not yet stood in a void and looked around. And there are, as it happens, a few real stars between the galaxies too. Not many, not dense, nothing like the interior of a galaxy, but not zero. Rogue stars, homeless stars, stars flung into the intergalactic dark by gravitational violence, drifting alone through space that holds almost nothing else. And there are stranger things still. Supernovae that explode with no host galaxy in sight, faint glows of homeless stars in galaxy clusters, ancient light from no particular address. But all of that is the next part of the story. For now, hold the image that the detective work gave us. A gas, too thin to touch, too hot for ordinary light, invisible to the eye, and nearly invisible to the telescope. And yet, when the universe's own instruments were brought to bear on it, when radio flashes and ancient photons and quasar light all carried their messages home, the gas was there. All of it. All those missing atoms. They had not gone anywhere. We had simply not yet learned how to ask properly. And there is something quietly hopeful in that. Not every absence is a true absence. Sometimes the thing that seems to have vanished is simply waiting for you to develop the right language to call it back. The intergalactic medium did not announce itself. It did not glow. It did not wave. It wrote its name patiently into every beam of light that crossed it and waited for us to learn to read. And in the first decades of the 21st century, piece by piece, we did. The fast radio bursts came. The quasar spectra were passed. The CMB maps were stacked. The Lyman alpha forest was decoded. And when it was all laid out, the missing half of the ordinary universe was accounted for, spread thin across the vastness between the galaxies, invisible and enormous and very, very hot. That is where we are now. The gas is found. The mystery of the missing baryons has, at least in its broad strokes, been resolved. But the resolution opens onto something even larger, because once you know that most of the ordinary matter in the universe lives in the intergalactic medium, you want to understand the structure that organizes it, the web that holds it all, the architecture of the cosmos that makes the gas pool in some places and leave others almost completely bare. And understanding that structure means understanding the voids as well as the filaments, the vast, near-empty spaces that make up most of the universe's volume, the places where the gas is thinnest, where the galaxies are fewest, where the dark between the threads is most absolute. So that is where we go next, into the web itself, not to the bright knots where the filaments tangle and the galaxy clusters form, not to the galaxies whose brilliance we have been gently unseating from the center of the picture, but to the web, to its threads and walls and the immense empty rooms between them, to the places that look at first like nothing, and which turn out, as this whole story has been turning out, to be something after all. And there it is, already assembled for us in the data. All those quasar spectra and FRB timing measurements and stacked CMB maps quietly insisting that the universe has a shape. Not a random scatter, not a fog, a structure. And once the missing baryons had been tracked to the intergalactic medium, the next natural question was the question of architecture. What holds the gas where it is? What determines where the threads run and where the emptiness begins? The answer has a name: the cosmic web. You have probably seen an image of it, even if you did not know what you were looking at. Those computer-generated pictures, threads of pale light stretching between bright knots, surrounding great dark bubbles, look like the inside of a soap foam or the nervous system of something vast and patient. They look almost biological. And that resemblance is not coincidental, not exactly. It emerges from the same mathematics that governs how things cluster under gravity, how a uniform medium develops structure over billions of years when every particle is pulling gently on every other particle, and the whole system slowly, irresistibly, collapses into the most efficient arrangement of mass it can find. The cosmic web is what gravity does to matter over cosmological time. Early in the universe, in the hundreds of thousands of years after the Big Bang, before the first stars lit up, matter was spread very nearly uniformly through space. Not perfectly uniformly. There were tiny fluctuations, ripples in the density, places where matter was just fractionally more concentrated than average. And those tiny seeds were enough because a slightly denser region pulled on its neighbors a little more firmly than average. Matter began to drift almost imperceptibly toward those seeds. The slightly denser regions grew denser still. Between them, regions that were slightly underdense lost matter to their neighbors and grew emptier. And over hundreds of millions of years, then billions, what had been a barely rippled near-uniform sea resolved into something utterly different. Long filaments, great flat walls or sheets of gas and galaxies, and surrounding vast enclosed volumes where matter had drained away to almost nothing. The voids. And at the intersections, the places where filaments crossed, where multiple threads tangled together, the density rose highest. Those are the knots of the web, the galaxy clusters. The places we have been for most of our astronomical history, paying almost all of our attention to. We mapped this structure over decades of hard observational work. The Sloan Digital Sky Survey, SDSS, a telescope in New Mexico that spent years systematically photographing millions of galaxies, measuring their distances, building a three-dimensional map of our corner of the universe, made the web something we could see rather than merely model. When you plot the positions of those millions of galaxies in 3 dimensions, the cosmic web leaps out at you. It is unmistakable. Filaments tens and hundreds of millions of light-years long, flat walls like great cosmic curtains, voids so large that the mind struggles to hold them, and the whole thing repeating, roughly self-similarly, at larger and larger scales, like a pattern that knows itself. We also built it in computers. Cosmological simulations carried the Millennium Simulation, later Illustris TNG, and Eagle take the known initial conditions of the early universe and the known laws of physics and simply run time forward, letting gravity and gas dynamics and the feedback from galaxies build structure from scratch. When those simulations finish running, the result looks almost indistinguishable from the observed universe. The web emerges. The same filaments and walls and voids appear in roughly the right proportions, in roughly the right arrangement. The match between the simulated web and the observed web is one of the great quiet triumphs of modern cosmology, a sign that we have the basic architecture right, even if enormous amounts of detail remain to be filled in. But mapping where the galaxies sit only traces part of the web. The galaxies are lighthouses. They show you where the web's densest knots are. What they do not show you, not directly, is the gas between the lighthouses, the filaments themselves, the whim that fills the threads and walls of the web between the galaxy clusters. To see that gas, you need different tools, the ones we talked about earlier. The FRBs, the quasar absorption lines, the CMB stacking. And when those are combined with the galaxy maps, a more complete picture of the web starts to emerge. The gas lives in the filaments. The filaments connect the clusters. The clusters are islands in a sea of gas. And surrounding the whole structure are the voids, the emptiest places in the observable universe. The voids deserve their own moment because the title of our journey tonight asks about a place where there are no stars, and the voids come closer to that description than almost anywhere else. Imagine a volume of space roughly 330 million light-years across. That is about 3,000 times the distance from the Milky Way to the Andromeda Galaxy, the nearest large galaxy to our own. 3,000 Andromeda distances across in every direction, and inside that volume compared to the average density of the universe. Almost nothing. Almost no galaxies, almost no filaments. Just the faint, thin tail of the cosmic web extending across the vast interior and an extraordinary, heavy, absolute darkness. This is the Boötes void. It is sometimes called the Great Nothing, and it is one of the largest known voids in the observable universe. If our own Milky Way were located somewhere near the center of the Boötes void, our nearest galactic neighbors would be so far away that even our most powerful telescopes, by the time astronomers had built them, might have struggled to detect them. We might have spent decades, perhaps well into the 20th century, convinced that the universe was almost entirely empty, that the Milky Way was, if not alone, then nearly so. The sky beyond our own galaxy would have seemed almost starless, not because stars did not exist, but because the nearest ones were so far away that their host galaxies would barely register. We live in a relatively well-populated part of the universe. The local group, our small cluster of galaxies, is part of a larger supercluster, embedded in a region of the web with reasonably dense filamentary structure. The Boötes void is a reminder that the universe is not uniformly furnished. Some rooms in this vast house are crowded, others are cavernous and nearly bare. And the voids are not a curiosity, they are most of the volume. When you count up the total space in the observable universe and ask how much of it is occupied by filaments, walls, and clusters versus how much is occupied by voids, the voids win. Overwhelmingly, the web, all those tangled threads and sheets, makes up a minority of the total volume. The great dark bubbles between the threads make up the majority. Emptiness, in this sense, dominates the universe's geometry. Matter dominates the web, but the web is the minority of the volume. This is one of the harder things to hold in your head about the universe. It is simultaneously mostly empty by volume and mostly not empty by mass. The matter is concentrated and stacked into filaments and sheets and clusters that take up relatively little room, and the rest is the void, almost but not quite bare. Almost but not quite. Because even inside the voids, the gas is not zero. The whim that fills the filaments thins dramatically inside the voids, from a few to a few hundred particles per cubic meter in the filaments to even fewer inside the void interiors. But it does not drop to absolute zero. Even the great emptiness of the Boötes void contains something. The particles per cubic meter there are so few they can barely be called a medium at all, but they are not nothing. In this universe, nothing has been extraordinarily difficult to find. The Hubble ultra-deep field is a case in point. Sometime in 2003 and 2004, the Hubble Space Telescope was pointed at a patch of sky so small and apparently so featureless that it had been deliberately chosen for its blankness, a patch roughly a tenth the diameter of the full moon, selected because it seemed to contain almost nothing interesting. The telescope was then exposed for the equivalent of nearly 1 million seconds of observation time, accumulated over many orbits, collecting every faint photon it could reach. The result was an image that contained approximately 10,000 galaxies, not stars, galaxies, each containing billions of stars spread across billions of light-years of depth, packed into what had looked like blank, empty sky. The great nothing, it turns out, was never nothing. The darkness between the things we could easily see was always full of things we couldn't yet see. What changed was our ability to look now. The title of tonight's journey asks about the place where there are no stars, and we have spent most of our time together talking about gas, the WIM, the filaments, the intergalactic medium. But the question of stars deserves a direct answer, because the answer, like so much else in this story, is not quite what you might expect. Are there stars between the galaxies? Almost none, but not zero. Let's take the inside of a galaxy cluster first, because clusters are the best studied environments for intergalactic space. Inside a rich galaxy cluster, hundreds or thousands of galaxies orbit in the cluster's gravitational well, passing close to each other, sometimes colliding, sometimes stripping each other of stars through tidal forces. And when stars get stripped, they do not necessarily fall into any particular galaxy. They drift. They become, in a precise sense, homeless. Stars that belong to no galaxy, orbiting the cluster's gravitational center in their own slow paths through the intracluster space. This faint population has a name: intracluster light. It was detected by looking very carefully at the diffuse glow between the galaxies inside clusters, a glow too spread out and too faint to come from the cluster galaxies themselves, but unmistakably there. It is the combined starlight of perhaps billions of individual stars, each one drifting alone between the galaxies, separated from any host by millions of light-years in some cases. They are not in any galaxy. They are in the space between. And supernovae, stellar explosions among the most violent events in the universe, have been observed detonating in that same intercluster space. A star that has been drifting alone between galaxies for billions of years, aging quietly in the dark, and at the end of its life going out in a blaze that has no galaxy to hide in. A supernova with no host. The explosion sitting in the image in an apparent void between the cluster galaxies, and yet undeniably real, undeniably bright. Beyond the clusters, in the great intergalactic stretches between them, the star count drops even further. But it does not reach zero because gravity, particularly the extreme gravity near the supermassive black holes that sit at the centers of most large galaxies, occasionally flings a star outward with enough velocity to escape the galaxy entirely. These are hypervelocity stars. They have been accelerated in a gravitational slingshot to speeds of hundreds of kilometers per second relative to their host galaxy, fast enough in some cases to exceed the escape velocity and travel outward into the intergalactic dark. They are moving so fast that they are effectively on one-way trajectories. They left home and they are not coming back. A hypervelocity star drifting through intergalactic space is an extraordinary thing to contemplate. A single star, a thing comparable to our own sun perhaps, or smaller, a long-lived star that will still be burning millions and billions of years from now, crossing the immense emptiness between the galaxies, alone at hundreds of kilometers per second, with no destination and no return. It is the loneliest imaginable traveler. So the answer to the title's question, be it where there are no stars, is that no stars is close but not technically complete. The voids are almost entirely starless. The intergalactic stretches between clusters hold only the rarest exiles. But inside the clusters themselves, drifting in the intracluster gas, there are stars without galaxies, a homeless stellar population, and occasionally a hypervelocity runaway crossing the dark between the threads of the web. But these stars are a rounding error on the rounding error. Stars themselves, all the stars inside all the galaxies in the observable universe, make up only something like 7 to 10% of all the ordinary matter in the universe. The baryons locked in stellar interiors are a small minority. The intergalactic stars are a small minority of that small minority. The universe's ordinary matter, its atoms and protons and electrons, is overwhelmingly not in stars, not even in galaxies. The ordinary matter is in the gas, in the WIM, in the filaments, between the galaxies, in the place the title names. This is the inversion that the whole of our journey tonight has been building toward. And I want to state it slowly and clearly because it is genuinely counterintuitive and worth sitting with. When you look at a picture of the universe, any of those beautiful deep field images, thousands of galaxies visible as small smudges and spirals and ellipses, your eye goes to the bright things, to the galaxies, to the concentrations of stellar light that have defined astronomy since the first telescope was pointed upward. Those bright things feel like the universe. They feel like the matter. They feel like the main event, but they are not even the ordinary matter. The intracluster medium in galaxy clusters, the hot gas between the galaxies inside the cluster, outweighs all the stars in all the cluster's galaxies by a factor of several. In a rich galaxy cluster, the stars are a small fraction of the ordinary matter even within the cluster's own boundaries. The gas between the galaxies right there inside the cluster is more massive than everything that is currently burning or has ever burned in that cluster's entire stellar population. And beyond the clusters in the circumgalactic medium, in the vast gas halo that surrounds each galaxy, extending out to distances of hundreds of thousands of light years, there is likely as much or more baryonic mass as there is inside the galaxy itself. The galaxy you see, the bright disk of stars and interstellar gas, is embedded in and surrounded by an enormous invisible cloud of gas that may outweigh it. You are seeing, in a galaxy image, the luminous minority of the system. Then, out in the intergalactic filaments, the WIM, the warm-hot intergalactic medium, lies the bulk of what was missing for so long from the baryon census. And when you add it all up, the WIM in the filaments, the circumgalactic halos, the intracluster gas, the cooler photoionized gas traced by the Lyman alpha forest, the picture that emerges is that somewhere between 50 and 90% of all ordinary matter in the universe today lives outside of galaxies. The galaxies themselves, for all their brilliance, are a minority. The shining parts of the universe are the foam on the ocean, not the ocean itself. 50 to 90% is a wide range, and I want to be honest about that. The exact partition is still debated. Different methods, the FRB dispersion measurements, the X-ray absorption detections, the CMB stacking, probe different temperatures and densities of gas, and they do not yet perfectly agree on how much goes where. The hot WIM at its peak temperatures, around 10 million Kelvin, is different from the warmer photoionized gas at 100,000 Kelvin, which is different again from the denser circumgalactic medium. Sorting out exactly how the baryons divide themselves among these phases is ongoing work. The broad headline, "Most ordinary matter is not in galaxies," is as settled as observational cosmology gets. The precise accounting by phase and temperature is live science, frontier science, the kind of question that gets answered one detection at a time. and detections are being made. The filaments of the cosmic web, those long threads of gas that the simulations drew, and the galaxy surveys traced indirectly, have now been directly photographed, glowing in their own faint light. Not just inferred, not just modeled, seen. In the years between 2019 and 2023, deep imaging programs using the hypersuprime cam on the Subaru telescope in Hawaii and using the MUSE spectrograph on the Very Large Telescope in Chile captured the faint emission of hydrogen gas, tracing the cosmic web's filaments around and between galaxies. The hydrogen glows in a particular wavelength, a specific red color called Lyman alpha emission, and the glow is so faint that imaging it requires extremely long exposures and extremely dark skies and very careful subtraction of all the things that might contaminate the signal. But it has been done. The web is no longer purely theoretical. You can, if you have the right instruments and the patience, look at it. What those images show is remarkable. The web is there, exactly where the simulations predicted. Filaments of glowing gas threading between galaxies, feeding them. The galaxies sit at the intersections or along the threads, embedded in the gas that is feeding them. The relationship between the web's gas and the galaxies it surrounds is not one of galaxies floating in a void, but of galaxies embedded in, sustained by, and to some extent created by, the flowing gas of the filaments around them. The bright islands are not independent. They are condensations on a larger fabric. This is, in a sense, the final nail in the old picture of island universes floating in void. The island metaphor implied isolation, self-sufficiency, a clear boundary between the island and the water around it. What we actually see is more intimate than that. The galaxies and the web are intertwined. Gas flows inward along filaments and feeds star formation. Supernovae and active galactic nuclides and the energetic black holes at the hearts of many galaxies blow gas back outward, enriching the circumgalactic medium and eventually the intergalactic medium with the metals forged in stellar interiors. The web feeds the galaxies chemically enrich the web. It is a cycle, and neither part is separable from the other. The ongoing observational campaigns are trying to map this cycle in increasing detail. The Rosetta telescope, an X-ray instrument launched in 2019, is scanning the full sky at X-ray wavelengths, building a map of the hot gas in clusters and in the intergalactic medium that is more detailed than anything achieved before. Early results from Rosetta have already detected the hot gas in filaments connecting clusters, providing direct evidence of the WIM at X-ray energies. The full sky census it is building will be an extraordinary resource for understanding where the baryons are and how they move. Looking further ahead, proposed observatories like Athena, a large X-ray space telescope designed to study the hot universe, and the Line Emission Mapper, known as LEM, a concept for mapping the emission from warm and hot intergalactic gas across the sky, represent the next generation of tools aimed specifically at this question. The mission to understand the WIMs, to go from we know it's there to we know exactly where it is, how much there is in each phase and how it moves, is not finished. It is well underway, gaining momentum, accumulating evidence, but it is not finished. The missing baryon problem, as a headline, is largely resolved. The answer is they are in the intergalactic gas, in the warm-hot medium of the cosmic web. But the detailed follow-up questions: how much is at what temperature? Where exactly along the filaments? How much is being driven outward by galactic feedback versus how much is pristine infall? How the circumgalactic medium transitions into the WIM? Those questions are the current frontier, each answered with a telescope, a spectrum, a careful analysis of a quasar's light or a radio burst's dispersion or the faint distortion of a CMB map. One detection at a time, one quasar spectrum, one FRB timing measurement, one careful image of a faint filament glowing in hydrogen light. That is how science works when the thing you are trying to see is a few atoms per cubic meter heated to a temperature no thermometer could survive in. Slowly, painstakingly, with instruments that push right to the edge of what is physically possible, and with the patience to wait for the technology to catch up to the question. So let us settle now into the whole picture. Let it rest for a moment before we come back to the simplest and most personal version of it. The universe, on the largest scales, is made of the cosmic web. Filaments of gas and dark matter stretch for tens and hundreds of millions of light years, meeting at dense knots where galaxy clusters form, surrounding enormous voids that make up most of the universe's volume. This structure assembled under gravity over cosmic time from tiny fluctuations in the early universe, the same fluctuations imprinted in the cosmic microwave background that the Planck satellite measured so precisely, the same fluctuations that Big Bang nucleosynthesis helped characterize in terms of what kinds of matter participated in them, the structure that the Sloan Digital Sky Survey revealed galaxy by galaxy, and that the Millennium Simulation and Illustrious TNG and Eagle reproduced in their computer-generated universes. The ordinary matter, the baryons, the atoms of hydrogen and helium, and all the heavier elements, the stuff that you and I and every star and planet and nebula are made of, does not follow the dark matter skeleton perfectly, but it follows it broadly. It concentrates in the filaments and sheets and clusters. It thins in the voids, and its total budget was fixed long ago in the first minutes after the Big Bang by nucleosynthesis, confirmed by the CMB, roughly 5% of the universe's total energy density, a small fraction of the total, but the total is vast, so even 5% is an almost incomprehensible quantity of atoms. For decades, when astronomers tried to count those atoms in the local universe, they could only find about half. The stars, the galaxies, the neutral gas clouds, the gas in clusters. Added together, it came to roughly half the expected total. The other half was missing. Not dark matter, which was a different accounting category entirely. Not dark energy, ordinary atoms lost. A genuine scandal in the cosmic ledger, persistent and puzzling and frustrating. The resolution came from understanding that the missing atoms were never in galaxies in the first place. They were heated long ago by the shock of infalling material as the cosmic web assembled, gravitational potential energy converting to heat as gas fell down into the web's filaments and knots. Additional heat came from galaxies themselves, supernovae exploding and pushing gas outward, active galactic nuclei, the luminous signatures of mass falling onto supermassive black holes, driving powerful winds that could carry gas hundreds of thousands and even millions of light years from the galaxies that generated them. This feedback enriched the gas with metals forged in stars. The intergalactic gas, that seemingly pristine emptiness, carries oxygen and carbon and neon and iron. Atoms that could only have been made inside stellar cores and then expelled outward into the intergalactic medium by the very galaxies they now surround. The gas is hot. Not heated in the way a cup of tea is warm. Not in a way you could feel, not in a way that could warm your hand. The temperature here means something very specific. The average kinetic energy of the individual particles. A particle of hydrogen gas in the WIM at 1,000,000 Kelvin is moving at a tremendous speed, hundreds of kilometers per second. But there are almost no particles, a few per cubic meter. The total thermal energy in any human-scale volume of the WIM is negligible. It would not warm a room, it would not even warm a breath. The heat is per particle, not per volume. Temperature and warmth are not the same thing when the density is that low. And that is how the universe's hottest, ordinary gas is simultaneously its best vacuum. Both facts are true, neither cancels the other. The WIM is simultaneously hotter than the sun's surface. and the surface not the core, and emptier than anything a laboratory on Earth can produce. A paradox that, once unpacked, turns out not to be a paradox at all, but a feature of what temperature really means at the extreme low end of density. We found this gas, despite its near invisibility, using 3 independent and beautifully specific methods. We used fast radio bursts, millisecond-long flashes of radio waves from distant cosmic events, whose different frequencies arrive at Earth at fractionally different times, the delay encoding the total number of free electrons the burst crossed. Jean-Pierre Macquart and his colleagues, using the Australian Square Kilometre Array Pathfinder, turned those timing measurements into a cosmic baryon census in 2020, the Macquart relation, and found that the full complement of missing baryons was there, spread through the intergalactic medium, consistent with the expectations from the CMB and nucleosynthesis. We used the spectra of distant quasars, searching for the absorption fingerprints of highly ionized oxygen. O7's oxygen with 6 of its 8 electrons stripped away by the heat, visible only in X-rays, to catch the hot WIM directly. Fabrizio Nicastro and his team published exactly this detection in Nature in 2018, using the quasar 1ES 1550-113 as a backlight and finding absorption from intervening filaments. We used the kinetic Sunyaev-Zeldovich effect, the subtle imprint that moving intergalactic gas leaves on the cosmic microwave background itself, detectable by stacking many CMB observations aligned between pairs of known galaxies, and found the gas signal between them in 2017 and 2018 consistent with the WIM. 3 methods, 3 different physical signatures, all pointing to the same reservoir, all consistent with the baryons being in the intergalactic medium. And now the web itself has been photographed. The structure that was a theoretical inference for decades, then a statistical pattern in Galaxies surveys, has been directly imaged in the emission of glowing hydrogen gas. The Hyper-Suprime Cam on the Subaru telescope and the MUSE spectrograph on the Very Large Telescope in Chile between 2019 and 2023 captured filaments of the cosmic web in emission. Faint, yes, demanding enormous observational effort, but there. The web is no longer something we model and infer. It is something we have seen. The picture, assembled from all of this, is this. The galaxies. All of them, every galaxy in the observable universe, with all their billions of stars, are points and threads on a larger structure. Bright condensations on a cosmic web. The foam on the surface of an ocean of gas. The gas is almost everywhere the galaxies are not. It holds, depending on how carefully you partition it and which phase you include, at least half, and probably much more than half of all, the ordinary matter in the observable universe. It is simultaneously the hottest diffuse medium in nature and the emptiest. It is chemically enriched by every generation of stars that has ever lived and died inside a galaxy. It is threaded through by the gravity of dark matter, shaped by the feedback of black holes, fed continuously by the slow infall of gas from void interiors. It is alive in a cosmological sense, not static, but flowing, cycling, evolving. And we are made of it. That is the most personal version of this story, and I want to linger there for a moment, because it deserves a slow breath. The atoms in your body and the oxygen you are breathing right now, if you are still awake and breathing slowly in the dark, the carbon that forms the backbone of every molecule in every cell, the iron carrying oxygen through your blood, those atoms were made in stars. Not the sun. The sun is not old enough or massive enough to have made the heavy elements. Earlier stars, stars that lived and died before the solar system formed, fused hydrogen and helium into heavier elements in their cores over millions and billions of years, and then, in supernovae, in stellar winds, in the slow exhalations of dying stars, released those atoms into the space around them. Some of those atoms stayed in the galaxy, in the interstellar medium, eventually incorporated into new generations of stars and planets, eventually into you, but not all of them. Many were expelled outward, carried by the same galactic winds and supernova pressures that heated and enriched the intergalactic medium into the circumgalactic medium and beyond, into the WIM, into the filaments of the cosmic web. They drifted there in the hot gas for a time. Some may have later fallen back, carried down a filament into a forming galaxy, incorporated into a new star, eventually into a new world. The atoms that make you are of the same family as the atoms in the intergalactic medium. The distinction between inside the galaxy and outside it is not a distinction between made of galaxies and made of something else. It is just a difference in where the atoms have traveled, what structures they have passed through, how long they have spent in each phase. Every atom in your body has a biography that stretches back billions of years and crosses scales from the nuclear to the intergalactic. You are not outside the cosmic web. You are a very local and very temporary condensation of it. The space between the galaxies, in the space where there are almost no stars, where the light is thin and the density is almost nothing, and the temperature is 1,000,000 degrees of almost empty hot, that space holds most of the ordinary universe. The atoms are there. Many of the atoms that were once there are here. Here in this room, in the air, in the blanket you have pulled up. In you, the emptiness and the fullness are not opposites in this story. They are the same thing seen from different angles. The universe is mostly empty by volume. The web's filaments take up a small fraction of the total space. The voids dominate. The Buddha's void and its cousins are the typical environment of the cosmos, not the exception. But the matter is in the web. The baryons are in the gas. The galaxies are the foam. And the foam is where we live. And the ocean is what surrounds us on every side, invisible and enormous, and very, very warm in its particles, and very, very sparse in its presence, and very, very full of the same atoms that we carry around in ourselves. We found this out slowly and carefully, using some of the most precise and creative observations in the history of astronomy. We timed radio flashes from distant catastrophes. We passed the spectra of the brightest objects in the universe, looking for the shadows of hot, invisible gas. We stacked thousands of maps of the Big Bang's afterglow, looking for a faint smudge left by moving electrons. We imaged, painstakingly, the faint glow of hydrogen in the dark spaces between the galaxies. And each time, what we found was not nothing. It was something, dense with atoms, hot with motion, old with history. The web is being mapped now in more detail than ever before by telescopes on the ground and in space. Erecita is building its full sky X-ray map. Future observatories, Athena in its design, the line emission mapper in its concept, are aimed specifically at the WIM, at understanding not just that the gas is there, but exactly where and how much and how it moves and how it changes. The census is ongoing. The question that tormented cosmologists for decades, where are the missing baryons, has been answered in its broad strokes. The more detailed answers are being assembled right now in spectra and timing measurements and maps that will take years to fully analyze. It is live science, the kind of science where the results are still being read, where the picture is still sharpening, where the full truth is not yet in hand but is coming clearer with each passing year. And that, in a strange way, is one of the most satisfying things to carry into sleep. The knowledge that the universe is still being discovered, that there are questions the smartest and most careful people on Earth are still working on, that the story is not finished, not even close, because we have found the missing atoms, but we still do not know in full detail how they got there. We know the broad mechanisms: gravitational shock heating, galactic feedback from supernovae, and active galactic nuclei. But the precise balance between infall and outflow, between pristine gas and enriched gas, between gas that has passed through a galaxy and gas that never has, those questions are at the edge of what we can currently measure. The cosmic web is not a static structure, it is evolving. More gas is falling in along the filaments even now. More gas is being expelled from galaxies even now. The web breathes slowly on billion-year timescales, and somewhere in the voids, the emptiest places in the observable universe, the places where even the thin gas of the WIM thins to almost nothing, there is a kind of absolute quiet. Not silence exactly, because silence implies an absence of sound, and in intergalactic space there is no medium to carry sound at all. A different kind of quiet. The quiet of enormous distance, of the near absence of matter, of a place where the universe has almost nothing to say for hundreds of millions of light years in every direction. That quiet is where I will leave you, at least for a moment, before we come back. Because somewhere you are listening to this, in a room perhaps, with a lamp still on or already dark, in a city whose lights are bright enough that you cannot see the Milky Way from where you are, or somewhere rural where the band of it is actually visible above you if you stepped outside, in a corner of the planet on a particular night in a particular season, and wherever you are, there is something worth knowing about the air around you, the walls, the ceiling, the blanket, the pillow. Every atom you can touch was made in a star. Every hydrogen atom in the water in your cells was made in the Big Bang itself, in the first few minutes of the universe, and has been part of the ordinary baryon budget ever since, counted in the ledger that the cosmic microwave background holds. The heavier atoms were forged later in stellar cores and expelled and drifted and fell into new structures, and eventually, after billions of years of movement and transformation and passage through the intergalactic medium and back, arrived here, in this room, in this moment. The ordinary matter that makes you up, all of it, every atom, has spent time in the intergalactic medium at some point in its history. Not you specifically, not this arrangement of atoms, but these individual atoms, these baryons that were always being counted in the ledger, even when they were temporarily missing from the census. They were in the filaments once, they were in the gas. They were part of the WIM, heated and stretched thin and drifting between galaxy clusters before some fluctuation of pressure or gravity or the slow infall of gas along a filament carried them into the region that would eventually become our galaxy, our solar system, this world. You are made of intergalactic gas that has come home. And the space between the galaxies, space with almost no stars, the space that looked from the outside like nothing, is where most of the universe's ordinary atoms still live. Patient, hot, thin, ancient. The ocean the galaxies float on. The galaxies are the foam. And you, wherever you are tonight, whatever corner of the world you are drifting in, you are a small and brief and somehow improbable concentration of the same stuff that fills the cosmic web, made of the same atoms, part of the same baryon budget, counted in the same ledger that was fixed by nucleosynthesis in the first minutes of the universe's life. That is not a metaphor. That is the literal truth, measured precisely, confirmed by quasar spectra and FRB timing and CMB maps and X-ray absorption lines, and the faint hydrogen glow of filaments imaged with telescopes in Hawaii and Chile. Carry that into sleep if you'd like. There is something quietly settling about it. Not lonely, the opposite of lonely. The ordinary matter is connected. The atoms in you have the same origin and the same accounting as the atoms in the most distant filament of the cosmic web. The separation is real. You are here and the whim is out there, but the kinship is also real. You are of the same ocean. If you are still with me and you have enjoyed this slow drift through the cosmic web, through the missing baryons and the million-degree vacuum and the photographed filaments and the rogue stars and the great nothing and the full, improbable, counterintuitive truth of what lurks between the galaxies, I would love it if you left a like or subscribed so that more nights like this one can find their way to you. Small creators like me rely on it genuinely, and every subscription helps keep the lamp on. And I would love to know, where in the world are you listening from tonight, and what time is it in your corner of the dark? Tell me in the comments. That question is always my favorite part. Close the books, dim the lamp. Class is over, sleepy scholar.